Hello and welcome to another Arlington High School Math 4 Honors lesson. I'm Kirk Weiler, and today we're going to be looking at Unit number 6, Lesson number 7, on basic inverse trigonometric functions. This is going to serve as the basis for our understanding on how to solve trig equations. And obviously, because trigonometric functions are so very vital to all sorts of branches of engineering and mathematics, it's important for us to also understand their inverses. And that's kind of tough, right? So we're going to do a review today of material that you should have seen in Algebra 2 with trigonometry in terms of the inverse trigonometric functions. And let's begin with an opening exercise. Alright, so exercise number 1 asks us to consider the function y equals the inverse sine of x. Okay? Now, letter A asks us to write an algebraic statement that's equivalent to y equals inverse sine of x. What I'd like you to do is I'd like you to pause the video right now and see if you can write an equation down that is identical to this but doesn't contain the inverse sine function. Pause the video now and see what you can do. Alright, well, if you understand inverses, then what you'll know is that this equation and this equation are more or less equivalent. I have to say more or less equivalent, and we'll kind of get into why that is eventually. But these things say the same thing, sine of y equals x. Now, given that this equation and our original function are the same, all right, then we ask letter B. Given your answer to part A, describe what the input x and the output y of this function represent. All right, and I think it's easier to understand that if you look at the equation circled in A than if you look at the original. Pause the video now and see if you can write down what the input x is and what the output y is. All right, let's go through it. Well, I want to go back and take a look at A and notice that the argument of the sine function, the thing that you're taking the sine of, is y. But the thing that's important to understand is that you can only have an angle as an input to a trig function, not an inverse trig function, but a trig function. So y must be an angle. That's what it must be. But x must be a sine value, right? With the normal sine function, x is an angle and y is a sine value. But here, y is the angle and x is the sine value. So going back to the original equation, the way that we would interpret this is that the output will be the angle that has a sine of x. All right? Now, letter C, what we want to start doing is we want to start thinking about what does the inverse sine function look like? And the first thing I'd like you to do is, use only about half of this space to do it, is draw a graph of just the sine function over in this portion. Pause the video now and go ahead and do that, and then we'll pick it up from there. All right, let's take a look. Gotta draw it kind of small, but we can fit it in here. Okay, so, and we'll do our typical negative 2 pi, negative pi, pi, 2 pi. Of course, we've got our pi over 2, our 3 pi over 2. Sorry, it takes me a little bit to dimension these. Negative pi over 2 and negative 3 pi over 2. Probably not going to do the greatest job drawing this graph, and I don't really need to, but remember, if I just plot points, then I get this beautiful trig curve. And if I plot points, I think I might be getting a little bit better at this, but only a little bit better. True artwork, not bad. All right, so there's our sine function. Let me label that. Y equals sine of x. Now, the second part of the problem asks us to restrict the domain and create a sketch of inverse sine and state its domain and range. So the real problem, right, is that the sine function is not one-to-one. And what we know is that non-one-to-one functions have inverses that are not functions. So what we want to do is we want to take the domain of the sine function, which is all real numbers, and we want to cut it down to size. We want to slice it up so that we preserve the range. We still have a range that goes from -1 to 1, but so that it is now 1 to 1. Now there are many different ways to do this, so what I'd like you to do is just pause the video right now and think of at least one way that you can restrict the domain of sine so that it still has the same range from -1 to 1, but it's now 1 to 1. Pause the video if you need to. Alright, let's go through it. Many, many different ways to do it. I'm going to switch colors real quick. Go over to red. The standard way of doing it is to restrict the domain from -π/2 to π/2. All right, that's the standard way. So the standard restriction is -π/2 to π/2. There are many others that work, but this is the standard, the conventional, and so it's the one that we're going to look at. All right, but you could also say from π/2 to 3π/2, or from -3π/2 to π/2. The reason that -π/2 to π/2 is chosen is because, number one, it's a continuous domain interval, right? It's all connected. And number two, it includes 0 to π/2. That's really critical. We want that. So now let's create the graph of inverse sine. Now, as you well know, to create the graph of an inverse, what you do is you just flip-flop ordered pairs. And there's three that are very easy. I can take the ordered pair 0, 0. And of course I can plot it as 0, 0. Here I could take the ordered pair π/2, 1 and plot it as 1 π/2. And I could take the point -π/2, -1, and I could plot it as the point -1, -π/2. Now how these 3 points are connected is a little bit tricky. Think about taking this red portion of the curve and reflecting it across the line y equals x. What you'd end up having is a curve that looks like this. Now truly, the inverse sine relationship, not the function, would continue to do this, all right? So it would kind of wind its way up the x-axis the way that the sine function goes along the, wind its way up the y-axis the way the sine function goes along the x-axis. Do you like the wave motion? But this is really the only portion that is in the true inverse sine. So what do we know? We know that the domain, do a nice little interval notation, will be -1 to 1, and the range will be -π/2 to π/2. Look, folks, and I want to be very clear about this, whether in my class or any other class, this is very, very important. All right? And the reason why is most people are completely okay with the idea that what the inverse sine gives out is an angle. Gives out an angle that has the sign that's in the parentheses. The problem is, because sine is not 1 to 1, there are lots of angles that have a sine of a particular value. For instance, if you just look at letter D, okay? Right, if we look at letter D, we would interpret this problem as saying, okay, find the angle that has a sine of 1/2. The problem is there's an infinite number of answers to that, but we can only give an answer that lies in this interval. And in fact, the only angle between -π/2 and π/2 with a sine of 1/2 is π/6. No other angle. All right? Likewise, the only angle between -π/2 and π/2 that has a sine of -√2/2 is -π/4. Now, I will always get students in my class that will say, well, look, I gave an answer of 7π/4. 7π/4 and -π/4, they're the same thing. Except they're not. They're just not. A negative angle and a positive angle aren't the same, but on top of that, this angle simply does not fit in this interval. It is not between -π/2 and +π/2. So no 7π/4, π/6, and -π/4. All right, I'm going to be scrubbing out the text in just a moment, so please copy down anything you need to. Pause the video if you have to. All right, let's move on to the exercise 2. No great surprise in exercise 2 and a follow-up exercise 2. Let's just pretend that's 2a and 2b. We're going to be working with the inverse cosine. So we're going to do exactly the same thing in exercise 2. What I'd like you to do is I'd like in exercise 2, the first one that is, for you to sketch the normal cosine, restrict its domain so that it maintains the range and also has the first quadrant in it, 0 to π/2. Then try to graph the inverse cosine and state its domain and range, because we're going to do it all together. Look back at exercise 1 if you need help. All right, but pause the video now. All right, let's go through it. A little bit quicker this time. All right, over here. Whoops. Over here, we're going to sketch our cosine. Negative 2 pi. Negative 3 pi over 2. Negative pi. Sorry, but you know how these things are dimensions, so we're not going to spend too much time on them. 1, negative 1, our cosine points. See how bad Mr. Weiler does? It's not too bad. It's not too good either, but it's not too bad. Besides missing that point down there, pretty good. Okay, so there's our cosine, right? How did you restrict the domain? Well, again, let's go red. I think it's really helpful, right? If we go from 0 to pi, then we now have a nice one-to-one function that includes 0 to pi over 2, preserves the range negative 1 to 1, and continues to be 1 to 1. Now, if that's then the function that we invert, here comes our inverse cosine. Okay, a little bit different. Let's take this point. What is that? That's the point 0, 1, right? So we're going to have the point 1, 0. All right? Here we've got the point pi over 2, 0. So that's going to give us the point 0, pi over 2. Here's the point pi comma negative 1, so we're going to want the point negative 1 pi. And just like the inverse sine, what we end up getting is a curve that looks like this. And again, whoops, I'm supposed to go through there. Really and truly, it kind of keeps going in this direction, but the only part of it that's the function is that part in solid blue. So we now can say that the domain continues to be negative 1 to 1, and the range, now the most important of them all, 0 to pi. Okay, again, make sure that you memorize or understand well enough how to develop these ranges, because this next problem all depends on it. So our second exercise 2, now we want to figure out the angle that has those 3 cosines, and that angle has to come between 0 and pi radians. So for instance, in exercise A, the inverse cosine of 1, well, that's equal to 0. It's the only angle between 0 and pi, inclusive, that has a cosine of 0. Or sorry, that has a cosine of 1. What angle has a cosine of 1/2? Well, that's going to be pi over 3. No other angles in that interval have that cosine. And the inverse cosine of negative 3/2, well, that's going to be positive 5 pi over 6, right? It's the only angle that has that cosine in that interval. Okay, that's why those ranges are so critical, and they're kind of annoying, but remember, they'll contain the first quadrant. They'll always contain 0 to pi over 2. The question then is, what else will they contain to get the whole range and to force them to be 1 to 1? So I'm going to scrub out the text in a second, copy down what you need to, pause the video. All right, here we go. Next page. I hear a loud cart rolling outside. So let's take a look at the last of the 3 major ones, right? The tangent graph. Now tangent's a little bit trickier, and notice I'm not asking you to graph it from negative 2 pi to 2 pi. There's a lot of redundancy in there. We're just going from negative pi over 2 to pi over 2. So what I'd like you to do is pause the video right now and see if you can remember, and it is a very good graph to know, if you can remember how tangent looks between these 2 x values. Pause the video now, look up in your notes if you need to, play around with it on your calculator, but see what tangent looks like. Okay, let's go through it. Tangent has vertical asymptotes at negative pi over 2 and pi over 2. We're not going to go through why that is. That was in the last lesson. And it looks something like this. It definitely goes through the origin, by the way, so that's my bad job of drawing. There we go. Goes vertical here and here. It does not go horizontal at the origin like y equals x cubed, but whatever. Now what we want to do is we want to create a graph of inverse tangent. This is a little bit different because I can't really plot points. I mean, I can, but I'm not sure how helpful it is. One thing I could certainly do is if 0, 0 is on the graph, it's on its inverse as well. Now here's the key. Since this graph has vertical asymptotes, this graph will have to have horizontal asymptotes. By the way, if you're wondering why I don't have to restrict the domain, it's because it's already 1 to 1 on this interval. So this is the standard restriction for tangent. All right, and tangent, then inverse tangent has a graph that looks like this. It's really kind of cool because it's one of the few graphs that sort of has 2 naturally occurring horizontal asymptotes. I'm not sure what's natural about the inverse tangent, but just roll with me on this. Now again, remember, quite possibly the most important thing, right? The domain now is actually all real numbers, but the range, and this is kind of neat, goes from negative pi over 2 to pi over 2, but we never get negative pi over 2 and pi over 2. That's the best we can do. All right? So, same deal in exercise 4. Now what we want to do is we want to be able to figure out the angles in that domain, right, or in that range, I should say. The angles that are in that range that have these 3 tangents. So, take a look at A, B, and C. Play around with these. Play around with the fact that tangent is sine divided by cosine, and see if you can figure out the 3 angles. Pause the video now. All right, let's go through it. Well, letter A, very, very important, right? Saying that an angle has a tangent of 1 is really saying that it's got the same sine and cosine. And the only angle between negative pi over 2 and pi over 2 where that's true is pi over 4. Now, saying that finding the inverse tangent of root 3, well, that means that originally what we must have had is we must have had the ratio of sine to cosine, right, whatever our theta are, must have been root 3 over 2 to 1/2. So what we really have to think about is what angle has a sine of root 3 over 2 and a cosine of 1/2? And that's an angle of pi over 3. Finally, maybe the hardest one, if we have an inverse tangent that's negative 1 over root 3, well, kind of thinking reference angles, right? It must have looked something like that, where, again, sine and cosine, right? So our reference angle is definitely pi over 6, but the tangent's negative, so we have to be down here, right? And in fact, what that means is that the inverse tangent must result in negative pi over 6. All right? So think about those a little bit. Pause the video if you need to, and then we'll scrub out the text. Are you all ready? Here it goes. All right, final page. Unquestionably, it is very important for you to be able to deal with the inverse sine, the inverse cosine, and the inverse tangent, no doubt. On occasion, you will also have to find the inverse secant and the inverse cosecant. Honestly, besides some very rare applications in calculus, I've never really felt the need to find the inverse cotangent. You never know, but I'll let another teacher deal with that at another time. Let's take a look at the inverse secant and the inverse cosecant. Now, I want to develop something right now. Apparently, I lost my pen. There we go. Hopefully that's the pen. All right, the inverse secant of 2. A lot of students immediately want to do like, oh, well, that'll be 1 over the inverse cosine of 2. No, that doesn't work. And actually, let me be very clear about this. That will not work. By the way, good luck anyway finding an angle whose cosine is 2. It's not going to happen. Let's explore this a little bit. Let's do the following. We know that whatever this is, it's going to be an angle. Let me call it theta. So what we know is that the secant of that angle must be 2. But think about it. That means the cosine of the angle must be 1/2. So in fact, whatever the angle is, the inverse secant of 2 must be the same as the inverse cosine of 1/2. So the reciprocal, and this is really quite neat, the reciprocal occurs inside of the inverse trig's argument, not outside. So the inverse secant of 5 would be the inverse cosine of 1/5. The inverse secant of 10 would be the inverse cosine of 1/10. But now this is pretty easy, right? Now we just go back to the inverse cosine, and the inverse cosine of 1/2 is pi over 3. All right? Try it with the inverse cosecant of negative root 2. All right, let's go through it. So hopefully this made enough sense to you to say, well, that must be the inverse sine of negative 1 over the square root of 2. You may not recognize this. If you don't, you may want to rationalize the denominator, but that would be the inverse sine of negative root 2 over 2. The reference angle is obviously pi over 4, but the inverse sine of a negative will leave us with negative pi over 4. Remember, only one output. These are functions. There can be only one output. So I don't want to see like, well, this angle, this angle, this angle, and this angle. Not happening right now. All right, I'm going to clear out the text in a moment, so copy anything down that you need to. And it's gone. All right. Well, this is Kirk Weiler, and it's been another Math 4 Honors lesson from Arlington High School. Thank you for joining me, and until next time, keep thinking and keep solving problems.